The A over R number that you can find printed on the compressor or the turbine housing of a turbocharger simply stands for area over ratio. The simplest possible explanation for this is that it's the size of the compressor and the turbine housing. The larger this number, the larger the housings, essentially the bigger the turbo. Now, this is a Garrett turbocharger, and these numbers you'll find printed as or cast as 0 point something or 1 point something on the larger turbochargers. As a very generic rule of thumb, mostly oriented at street and stock applications, here's a little cheat sheet that gives you the sort of AR numbers that you can expect in relation to engine displacement. Now, some other manufacturers won't be using numbers like this, they'll be using centimeters squared. And here's another little cheat sheet that converts Garrett-style AR numbers, which are actually ratios, to centimeters squared numbers. So, these tell you about the size of the turbocharger. But where do the numbers come from? How are they obtained? Well, you can actually calculate them, not very accurately, but we can try. Area over ratio stands for the cross-sectional area, which you can really only measure right here. If we're doing the compressor, at the inlet of the compressor, we have around 30-ish millimeters. Because this is Garrett, it's going to be inches, so the radius is 15 millimeters, which is this much inches, and cross-sectional area is pi radius squared, which gives us this number. The radius, so area over radius, the other radius comes from the center, so from the very center of the turbo axis, or the center of the compressor wheel, up to the center of that cross-sectional area. And as far as I can tell, that's around 76-ish millimeters. Very hard to be accurate with your hands moving around free like this. If we convert that to inches and then divide these two numbers, we should get something close to 0.43 AR, which is what's cast right here on the compressor housing. To understand what A over R numbers mean in terms of performance, all you have to do is think of your thumb blocking off some sort of hose. The more you block it off, the faster and with greater pressure the fluid comes out, which means that we are enabling a higher gas velocity. The higher the gas velocity, the better the turbo spool up, which means that the small A over R numbers improve engine responsiveness and turbo spool up at low RPM. However, as RPMs increase, we are increasing the maximum volume we are trying to push through a reduced opening, which means that small A over R housings at high RPM create an obstruction. They essentially choke the engine and reduce top end performance. Now, if we increase the A over R on the housings, we are increasing the cross section, we are creating more space, which means that we can push a greater maximum volume of gas. However, a greater opening cross section always reduces gas velocity, which means that at low RPM, when we have small gas volumes, we are going to have less responsiveness and a more lethargic engine and reduced turbo spool. And this is why typically stock and street-oriented applications are going to have smaller A over R numbers, because for them, low RPM performance, transient response is very important, but racing engines are typically going to have larger A over R numbers because for them, low RPM performance isn't that important because they spend most of their time at high RPM. Boost threshold is a term that is often mistaken for boost lag or turbo lag. Boost threshold is the engine speed or RPM at which your turbocharger starts producing significant boost. Let's imagine that's 3000 RPM. Boost lag is the delay in torque delivery in engine response when you open the throttle from a closed throttle while you are above your boost threshold. So let's imagine the throttle is closed and you floor it while you are at 3,500 RPM, and the little delay in response, the little delay in the burst of torque, that's your boost lag. Replacing your turbine housing with a turbine housing that has a smaller A over R number is going to reduce your boost threshold. You're going to reach it sooner because it's going to increase your exhaust gas velocity, and that's going to get your turbine wheel and your compressor wheel, because it's connected to the turbine wheel, up to the speed where the compressor wheel can produce significant boost sooner. However, a turbine housing with a smaller A over R number is not going to have a very noticeable impact on boost lag. To reduce boost lag, you need a turbine wheel and a compressor wheel that are smaller or made from a different, lighter material, which is going to reduce their inertia, which means they will respond better to sudden changes in rotational speed, which occur when you open and close the throttle. Whenever we have something spinning inside of something in a vehicle, we tend to have bearings supporting a smooth and long-lasting rotation, and the shaft inside a turbocharger, which is cast as part of the turbine wheel and onto which the compressor wheel is bolted, is no exception. Turbos can have journal or ball bearings. As a rule of thumb, journal bearings tend to last a bit longer because they bear loads a bit better, but that's only the case if they receive a constant pressurized supply of clean oil, which is changed at regular intervals. Ball bearings, their only real drawbacks are that they offer a very slightly reduced lifespan and that they're more expensive, but they also offer a reduced rolling resistance, which means that they can reduce both boost lag and boost threshold. Typically, they reduce boost threshold by 100, 150, maybe even a bit more RPM, whereas their effect on boost lag can be even more noticeable. The added benefit of ball bearings is that they require less oil, so they tend to have oil restrictors in the oil inlet, which means that there's also less oil coming out from the turbocharger and going back to the engine through the oil return, which means that setting up oil return can be easier with a ball bearing turbo because there's less risk of the oil coming back up and you getting a smoky turbo. Another benefit of ball bearings, which offers reduced rolling resistance, is that they don't require thrust bearings. To bear axial loads, journal bearings also need a thrust bearing, whereas the center section, a ball bearing center section, can bear both radial and axial loads. CHRA stands for Center Housing Rotating Assembly, and it's this that I'm holding in my hand. It is essentially the core of the turbocharger. It is the turbo minus the compressor and the turbine housings. Replacing just the center housing can be a very fast way to rebuild the turbo because you just swap the cores. It's also cost effective because you can reuse these two housings because they don't really see any wear unless the turbo blows up or something. And you're also saving on shipping costs because these tend to be the largest and heaviest parts of the turbo. On the compressor wheel, the air comes in through here and it exits through here. So that means that this is our inducer. This is the part of the compressor wheel that bites into the air. As the wheel rotates, the shape of the blades forces the air towards this lower part, which means that this is our exducer, or the part that spits out the air. Increasing the size of the inducer while keeping the exducer the same will increase the maximum potential airflow and thus peak power because it makes the compressor wheel take a bigger bite of air with every blade. The downside is that it causes the turbo to spool up a bit slower because taking larger bites of air means that there's more resistance and more work that the wheels must do. But a greater problem with overly large inducer diameters is that it can lead to surge, which can damage the turbo. Increasing the size of the exducer while keeping inducer size the same has the opposite effect. It makes the turbo spool up faster or reduces the boost threshold because it increases the gas speed. This happens because air is being spit out radially. So a greater exducer diameter means that we have a larger wheel edge speed for the same shaft speed. Because with a larger diameter, the outer edge must cover a greater distance within the same time, leading to increased velocity. This increased wheel edge velocity means that the gases exit at much higher speeds, which means that the turbo builds boost faster. Another benefit of an increased exducer is the ability to support a higher boost pressure. But note that these effects of an increased exducer diameter have diminishing returns, so don't expect to see something like this on a turbo. This would just be very heavy and would have massive boost lag. Now, if we divide the smaller diameter, or the inducer, with the larger diameter, or the exducer, and square this value and then multiply it by 100, we will get the trim of the wheel. The trim is an indication of how close the inducer and exducer are to each other. The closer the inducer and exducer diameters are to each other, the higher the trim number will be, with 100 being the maximum possible trim number. However, you will never see 100 on an actual turbo because that would mean that the inducer and exducer are of the same size and that wouldn't work at all. In reality, most compressor trim numbers are somewhere between 45 and 65. There are exceptions, of course, but most are in that range. A higher number means that we have increased maximum airflow capacity, so increased peak power, at the expense of an increased boost threshold. So if you take a compressor housing with a small a over r and combine it with a compressor wheel with a small trim, you can expect to have a very low boost threshold, or to build peak boost at very low RPM. Now, the trim for the turbine wheel is calculated using the same formula, but remember that for the turbine wheel, the inducer is the larger diameter and the exducer is the smaller diameter. This is because the air comes in and out in different directions at the turbine wheel. Turbine trim numbers will also be much higher compared to compressor trims, usually ranging somewhere between 75 to 90. This is because we have different airflow dynamics on the turbine side. We don't have to worry about surge, and we want to maximize the blade area for grabbing the exhaust gas in order to maximize the energy imparted onto the turbine wheel. Turbine trim changes have a less noticeable effect on performance compared to compressor trims, which is why a turbocharger model will usually offer multiple different compressor trim options and often just one turbine trim. In addition to inducer and exducer diameters, compressor wheel blade design and number of blades play a major role in turbocharger performance. This compressor wheel is a typical modern design that employs splitter blades. A design like this leaves more room between the main blades, which allows a bigger bite of air, which allows improved efficiency and better airflow, especially at high RPM, because it leaves more space for the air to pass through. So a compressor wheel like this one is well suited for high RPM performance and allows a higher peak boost pressure at the expense of a slightly increased boost threshold. Stock applications will often combine a splitter blade design like this one together with a small trim on the wheel and a small A over R on the housing to create a good compromise between responsiveness and high RPM performance. On the other hand, aftermarket and racing applications sometimes employ a design that has an increased number of main blades, but without any splitter blades. A design like this improves spool up because there's more blades biting into the air and pushing it into the engine. This design does sacrifice a bit of peak power because there's less space for airflow through the wheel since more of it is occupied by blade mass. But combining a wheel like this with a large A over R and a large trim reduces the boost threshold in a racing application while maintaining top-end performance. A small drawback of wheels with an increased main blade count is that they tend to be slightly heavier than splitter blade designs due to the increased amount of material present. This can slightly increase boost lag, but the effect is rarely noticeable in practice. A modern and beneficial design feature that this compressor wheel does not have is called an extended tip. An extended tip refers to a special machining technique employed on the exducer end of modern compressor wheels. Material is removed from the very bottom of the exducer but left at the top of the blades. This allows the wheel to harness the improved spool benefits of an increased exducer diameter, but without the added rotational mass which negatively impacts boost lag. Another major improvement in compressor wheel design has occurred on the back. Early compressor wheels employed a flat back design. This design demonstrated an inability to deal with the stresses of high RPM and high boost pressure which caused flat back wheels to fall apart. A super back design increases the amount of material at the base, which dramatically improves strength without increasing the weight too much. A major advancement in more modern turbochargers has been the introduction of superior materials and more advanced machining techniques. Whereas early compressor wheels were usually made by machining a near-net casting, more modern, performance-oriented ones are often machined from a solid billet. A billet or a forging has a superior, more uniform internal structure, which means that the shaft of the wheel as well as the blades can be made thinner, which makes the wheel lighter while at the same time allowing more space for airflow through the wheel, which means that we are at the same time reducing boost lag and improving high RPM performance. On the turbine side of things, we not only have the same improved manufacturing techniques, but we also have the introduction of super alloys beyond the now well-known Inconel. Super alloys like MAR-M and titanium aluminide have allowed even lighter turbine wheels with an even higher temperature resistance. This makes them especially suited for high-performance gasoline applications, whose lower compression ratio and different air-fuel ratios create exhaust gas temperatures that can be more than 100 degrees higher compared to an equivalent diesel engine. Now the turbocharger needs to be connected to the engine at the exhaust manifold, so that's the turbo inlet, goes to the exhaust manifold, that's the turbo outlet, goes to the downpipe, and here we have the turbo intake side outlet. This goes to the intake manifold of the engine, and here we have the turbo inlet. The air filter piping from the air filter goes here. This is where the air comes in, and here the air comes out. Now the intake side stuff is usually flexible hoses, relatively simple connections. However, the exhaust stuff is rigid bolt connections with specific flanges. And I'm sure you've heard of terms like T2, T3, T4, and so on. These are simply different flange measurements for different turbo sizes. On the downpipe, we also have stuff like 4-bolt, 5-bolt, and so on. Again, just flanges, really nothing to explain here other than the fact that you have to make sure that the flanges on your exhaust manifold and downpipe match the flanges on your turbo. Something that can be considered an improvement, which we can see on this turbo on both the downpipe and the connection to the center housing, is a V-band connection. Now this one is with 2 bolts. It's not what you're typically going to see on aftermarket applications. For example, it's usually going to be just 1 bolt, but it's an improvement because number 1, it saves space. It allows a more compact connection. And number 2, this is less susceptible to the bolts rusting and becoming seized and impossible to remove. So it's usually easier and faster to remove the turbo because there's less bolts. The pressure ratio of a turbocharger is a more accurate measurement of the amount of boost that a turbocharger actually generates. Pressure ratio numbers enable a better comparison of different turbochargers by isolating their performance from external factors such as altitude above sea level or different intake air setups. Pressure ratio is calculated by adding the boost pressure of the turbocharger, which is the pressure generated by your turbocharger above atmosphere. We add this to absolute atmospheric pressure and then divide this by absolute atmospheric air pressure. If you have a completely stock intake system and air filter, then you remove 1 psi or 0.07 bar from this number. So if we assume that we are at sea level, and if we assume that our turbo is generating 14.5 psi or 1 bar of boost, for example, then our pressure ratio is 1.98, which is essentially 2. You can consult the compressor map section of this video to see why pressure ratio is important. Surge or compressor surge occurs whenever the turbo is trying to stuff more air into the engine than the engine can swallow. This causes reverse pressure waves coming from the intake side of the engine back to the turbo, and it can damage the turbo. The easiest way to cause compressor surge is to install a turbocharger that is simply too big for the engine. We have to distinguish between two kinds of compressor surge. The first one occurs when the engine is under load, so when the throttle is fully pressed. The second kind of surge occurs only when the throttle pedal is released. Both of these can be destructive if they're strong enough, but surge that occurs under load is more dangerous and causes greater damage much faster. The easiest way to get rid of surge that occurs when you release the throttle is to install a blow-off valve. This converts the sound coming from the engine when you release the throttle from this to this. To get rid of surge that occurs when you press the throttle pedal, you can either reduce the boost pressure or install a smaller turbocharger. Something else that can help is an anti-surge housing like this one, which has these ports, which basically act like an escape path for the reverse pressure wave, so they can eliminate or at least reduce compressor surge. A compressor map like this one may look very daunting and confusing at first glance, but it is probably the most efficient tool for choosing the correct turbocharger for your application. Now, to make reading compressor maps completely non-intimidating, I will give you some pretty disgusting but also very useful hacks. This is a map for a Garrett GT2871R, a pretty old-school design by modern standards, but still a very popular choice for many four-cylinder engines. On the x-axis, here we see airflow in pounds per minute. Now remember, airflow is what makes power. The more air we can put into the engine, the more power we can make. So to make things more simple and intuitive, you can multiply all these numbers by 10. And imagine they are horsepower. This is not 100% accurate, but it is 99% accurate and more than accurate enough for enthusiast level or amateur racing purposes. Our y-axis is our pressure ratio. Remember, when the turbo added 1 bar of boost at sea level, our pressure ratio was 1.98. Let's say that's 2. That means we can convert pressure ratio into turbo boost. So a pressure ratio of 2 is 1 bar of boost, or 14.5 psi. 2.5 is 1.5 bar of boost, and 3 is 2 bar of boost. Again, not 100% accurate, but very, very close. These are your efficiency islands. And you want to be somewhere here in the top efficiency island where the turbo is most happy and most efficient. The more efficiently a turbo operates, the less heat it adds to the air and the more power we make. This is your surge line, and this is your choke line. So with our hacks, we can see right off the bat that this is a turbo suitable for a maximum of up to about 480 horsepower at close to 1.5 bar of boost. But this is very close to the choke line, and the turbo will struggle to live a long and happy life here because, as we can see, this is very near the shaft speed limit, which will lead to premature failure. If you want to make more than 400 horsepower, this is not the turbo for you. As we can see from the compressor map, what this turbo actually wants to do is to make around 300 horsepower at about 1.25 bar of boost. This is where its peak efficiency is, and here it will perform at its best. Now, I'm actually running a clone of this very turbo on my project car, which is a 1987 Toyota MR2 with a 1.6-liter 4AFE Toyota engine, making around 300 horsepower. Of course, to make 300 horsepower from such a small displacement, I had to run 2 bar of boost pressure. If we plot this on our compressor map, you can see that I'm actually behind the surge line, which means that I should be experiencing surge. But in practice, there is no surge at all on my setup. The reason behind that is because the turbo I'm running comes from a company called Max Speeding Rods, which makes a budget-friendly version of this turbo. But what's interesting is that they decided to slightly tweak the design to make their turbo suitable for smaller engine displacements. Here we can see the original Garrett specs and the modified Max Speeding Rod specs. The Max Speed turbo uses a smaller inducer, which results in a smaller trim within the same compressor housing A over R. On top of this, they replaced the original splitter blade Garrett design with a 9 main blade only design. Overall, this leads to a slightly faster spool up at the expense of reduced flow at high RPM. It is precisely this reduced flow of the modified compressor wheel that keeps me out of surge at high RPM while helping the turbo feel less like it's too big for the engine at low and mid RPM. For comparison's sake, here's what a more modern and much more expensive turbo can do. This is the Garrett G25 550. Due to its improved wheel aerodynamics and more modern overall design, it's more efficient pretty much everywhere and can easily sustain higher power and boost levels, while at the same time it doesn't surge on smaller engines running high boost. This is a regular turbine inlet. This is a twin scroll inlet. Let's imagine we have a 4-cylinder engine. With a normal single scroll inlet, all the exhaust pulses from each of the cylinders are directed to the turbine wheel through a single entry point. So if we have a firing order of 1, 3, 4, 2, we can end up in a situation where the exhaust pulse from cylinder 3 is being released from the engine while the exhaust pulse from cylinder 1 is entering the turbine inlet. This means that exhaust pulse from cylinder 1 has increased the pressure in the exhaust manifold and is interfering with the pulse from cylinder 3, making it harder for this pulse to reach the turbine inlet. This interference between cylinder pulses reduces their effectiveness in driving the turbine wheel, which can negatively impact spool up and overall performance. With a twin scroll setup, we separate the cylinders. This separation of cylinders extends from the exhaust manifold into the turbine housing. In other words, each pair of cylinders gets its own scroll and entry point. This means that we double the time between exhaust pulses in an individual scroll, which eliminates the possibility of the pulses mixing and interfering with each other. We also increase the speed of the gases, which positively impacts spool up. In general, a twin scroll setup will spool up faster and usually perform better across the rev range, but its effects will be more noticeable at low and mid RPM. The only real drawback is that a twin scroll setup needs a special exhaust manifold and turbine housing, which may be unavailable for some engine platforms. When they are available, they increase cost and complexity. This turbocharger is equipped with an internal wastegate in its turbine housing. As you can see right here, an internal wastegate is essentially a trap door, which remains closed until target boost pressure is reached. When it is reached, it opens and allows a portion of the exhaust gases to escape before they reach the turbine wheel. This prevents the speed of the turbine wheel from increasing any further, which prevents overboost and damage to the turbo, and also allows boost to be maintained at the desired target level. Now, the wastegate arm itself is controlled by a wastegate actuator. Now, this is a pneumatic wastegate actuator, which means that it can be controlled either by vacuum or by boost. If you tried pulling it out and you can't pull it out, that means you can push it in, which means that this is a vacuum-controlled wastegate actuator. If you try to push it in and you can't, but you can pull it out, then it's a boost-controlled wastegate actuator. And sure enough, if we connect a tiny little handheld vacuum pump to this, you can see that getting some vacuum is going to make this move. And also we can see it on the turbo itself. A wastegate actuator does not have to be pneumatic. It does not have to be controlled by boost or vacuum or anything. It can be fully electronic. So basically a servo motor or something similar controlled directly by the ECU. And this allows a non-linear, more accurate and more advanced control of the wastegate. Now, a wastegate also doesn't have to be internal. It can be external, so not part of the turbine housing, but a separate device on the exhaust manifold. Now, the benefits of an external wastegate is that it allows a finer, more advanced, more accurate, more consistent boost control, and it's not susceptible to being forced open under normal operating conditions, which means that it's going to stay perfectly shut until target boost is reached, which means that target boost will be reached faster and controlled more consistently. The only real drawback of an external wastegate is increased cost and complexity. Now, a turbocharger does not necessarily need to have some sort of trapdoor, aka a wastegate, to control boost. There is a different way of controlling boost, and it is called VGT or VNT, and that stands for variable geometry turbo or variable nozzle turbo. Now, that is a slightly more complicated system that does not involve any kind of trapdoor, as we said, but instead it is based again on a lever that is again controlled by some sort of pneumatic or electronic actuator. But this time, instead of a trapdoor, we have a ring, which is operated by the little lever, and that ring then operates a series of little blades. At low engine speeds, the blades or the vanes are open just a little bit. This reduces the cross-section of the entry into the turbine housing, and as we already know, if we reduce the cross-sectional area of a passage, the speed of the fluid going through that passage will increase. Increased exhaust gas speed also increases turbine speed, which helps the turbo spool up noticeably faster at low RPM. As engine speed increases, the vanes open more and more to reduce restriction and allow a greater volume of gas to pass. When they're fully open, the cross-sectional area is actually too large, so essentially they act like an overly large AR housing, which reduces the speed of the exhaust gas to the extent that it prevents the turbine wheel from further increasing its speed, allowing it to maintain desired boost pressure. A VGT turbo is essentially like a turbo with a variable A over R turbine housing. At low RPM, we simulate a very small A over R, which helps increase spool up and engine responsiveness. But as the RPMs increase, we increase the A over R of the turbine housing, allowing a greater volume of gas to pass through, and so we also improve performance at higher RPM. This means that a VGT system is very much beneficial for performance, and it improves performance and responsiveness over a relatively wide range of RPM. So you could say that this is superior to a conventional wastegate. So the question is then, why do we see VGT turbos pretty much exclusively on diesel applications, but almost never on gasoline applications? Well, as we know, gasoline engines have an increased exhaust gas temperature. And as you can see, this system is kind of flimsy and kind of delicate, which means that to work at increased exhaust gas temperatures, it needs some very exotic and expensive materials, which means that it is really not a cost-effective solution. So we only see it on stuff like a Porsche, and maybe someone else, which is a luxury high-performance gasoline vehicle. And there you have it, the Turbo Dictionary. Hope you found that useful. And as always, thanks a lot for watching. And I'll be seeing you soon with more fun and useful stuff on the D4A channel.